Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Delhi University. Today we are going to discuss about the module Introduction to Nuclear Energy from paper Energy Related Materials. So students, let us discuss or see what are we going to learn from this module. First, we will learn about the fission energy, next about the fusion energy. Then we will discuss about how does a neutron interact with the matter, neutron production sources, macroscopic cross section. Lastly, we will discuss about the neutron flux and neutron fluence. Before starting with this module, I will give you some introduction about the nuclear energy. There is no doubt that energy resources for electricity generation are essential for the technological growth of the human civilization. It plays a crucial role in economic growth and development, and hence our modern ways of life. On the basis of recent surveys, it has been estimated that the world energy requirement will be nearly double by the year 2040, which must be fulfilled through energy resources besides the fossil fuels. The greenhouse gas emission into the atmosphere and climatic situations are significantly influenced by the use of these fossil fuels. Though several research groups have been tried to make fossil fuels based power generation cleaner, however, they alone cannot make significant change in the present problem. Hence, several countries and the eminent research groups have recognized the importance of clean and emission-free nuclear energy. There are several established technologies which are more than ready for the utilization of nuclear energy. The application of nuclear energy for electricity generation differs widely in various countries of the world. France produces about 79%, whereas Switzerland, Ukraine, South Korea, Japan, and the United States of America produces about 48%, 40%, 35%, 30%, and approximately 19% of the total energy from nuclear power plants. India and Brazil depend on the nuclear energy for only about 2.5% and 2.8% respectively of their energy needs. It is noteworthy that fast-growing countries like India, China, and Brazil produces comparatively less power from the nuclear plants. Hence, there are marvelous opportunities for nuclear energy growth in such countries. Nuclear energy has been produced through nuclear reactors. Nowadays, there are about 440 nuclear reactors worldwide, producing 17% of the world electricity requirements. Amongst them, 140 nuclear reactors are in the USA only. The first radioactive chain was first successfully initiated in 1940 at the University of Chicago. The nuclear fuels shows an impressive growth since then. following happenings such as reduced public confidence in nuclear energy and in nuclear power industries saw lack of progress. However, US government's decisions to improve energy security through boosting nuclear energy production has reawakened much hope for the renewal of the nuclear power industries in USA and in the whole world as well. As the possibility of the nuclear based energy is expanded, the materials used in the production of nuclear energy has emerged an important role and received special interest in the research of materials of nuclear energy. Furthermore, the recent discussions activities happened in Japan. The recent disastrous activities happened in Japan due to tsunami and earthquakes, putting questions, suggestions of protections, and investigations of highly resistant materials. In this chapter, it is devoted to addressing the several interesting, fundamental, and application aspects of materials which are used in nuclear reactors for nuclear energy production. Nuclear fission. The nuclear fission is the process in which a heavy nucleus or heavy radioactive atom breaks into two or more smaller nuclei and thus releasing certain amount of energy. From figure below, we can observe that heavier nuclei have smaller binding energy compared to those in the middle of the periodic table. Hence, nuclear fission is highly favorable for heavy nucleus. The nuclear fission contains splitting of heavy nuclei materials such as uranium-235 or plutonium-239 using striking of a neutron. Nuclear fission is the most usual process of producing the bulk amount of energy. The natural uranium is most important fuel for nuclear fission, which contains 99.3% of 238 uranium, approximately 0.6988% of 235 uranium, and approximately 0.0122% of 234 uranium. In nuclear fission reaction, a stray neutron strikes on an atom of U-235, gets absorbed by it, and results to the formation of an unstable atom of 236U, which then undergoes fission by creating two smaller atoms of different mass, releasing 2.5 neutrons on an average and liberating an average amount of 193.5 mega electron volt as shown in the figure below. In fission reaction, the fission fragments are slightly moved from fission points and the energy released transformed into heat. The fission reaction of U-235 can take place in 30 different ways while creating 60 different kinds of fission fragments. A generally accepted fission reaction is explained by the following reaction. 235U plus 1 neutron gives 92 krypton plus 142 barium plus 2 neutrons plus some amount of energy. This equation represents the fission of one U-235 atom after striking a slow neutron leading to fission fragments krypton-92 and barium-142, an average release of 2 neutrons and energy. The radioisotope 235U, which is used as a nuclear fuel material in nuclear fission, is the only naturally occurring isotopes that can be induced by stray neutrons. Besides 235U, 239Pu, and 233U are also used as fissile atoms. However, they are not naturally occurring radioisotopes. They are produced by neutron absorption reactions of 238U and 232Th respectively. Both 238U and 232Th are called as fertile atoms and can also undergo nuclear fission, but only by fast neutrons with high energy of 1 megaelectron-volt. Hence, these radioisotopes are sometimes called as fissionable. Nuclear fission chain reaction. As discussed earlier, the fission of 235U atoms create an average of 2.5 neutrons. Hence, to withstand a nuclear fission chain reaction, these neutrons must be able to initiate the nuclear fission of another 235U atom. The schematic of nuclear fission chain reaction of 235U atoms is shown in the figure. About 99.23% of neutrons released instantaneously, that is within 10 to the power minus 14 seconds, due to fission reaction of 235U atoms, which are known as prompt neutrons, and the rest, about 0.75%, released, which are over a longer period of time, that is over 20 seconds, are called as delayed neutrons. However, the delayed neutrons serves an important part in monitoring the nuclear fission chain reaction. The neutron's economy plays an important role in the design of a nuclear reactor. The promising neutron economy requires few definite conditions must be met by chain reaction system. For a known geometry, there is a certain minimum size or critical size of chain reacting system in which neutrons generation by fission reaction stabilizes the loss of neutrons by leakage, and the fission chain reaction can sustained individually. On the basis of comparative generation and loss of fission neutrons, the reactor can be classified in 3 different phases. First, subcritical, loss of fission neutron more than the generation. Second, critical, balance between fission neutron and loss. Finally, the third one, supercritical, where there is generation of fission neutrons is higher than loss. Nuclear fission chain reaction. These figures shows the examples of the various nuclear fission chain reaction. On Earth, nuclear fission chain reactions takes place in nuclear reactors, which use controlled chain reactions to generate electricity. The last figure shows the uncontrolled chain reaction which takes place during the explosion of an atomic bomb. Nuclear fission products. The products of nuclear fission reactions are radioactive, but the energy released from these reactions is less harmful to the environment than the use of fossil fuels. As you can see in this cartoon which has been shown, which is saying that nuclear power is a good temporary option while we develop wind and solar power. The products are intensely radioactive and must be treated and or stored. Nuclear fusion. The nuclear fusion is essentially the reverse process of nuclear fission in which light nuclei are combined together or fuse to form heavier nuclei and thus releasing huge amount of energy in the process. Nuclear fusion is main process which powers the sun and the stars and also a major source behind today's nuclear technology of generating nuclear energy. The reaction of combining deuterium, that is heavy hydrogen, and tritium, heavy hydrogen, to create helium, alpha particle, and neutron is the easiest fusion reaction that can be carried out in laboratory as shown in the figure. The fusion reaction of 1 kilogram of deuterium and tritium can produce energy 1000 times higher than the energy produced via burning of 1 kilogram of fossil fuel even without emitting any greenhouse gas. The easiest nuclear fusion reaction is given by the following reaction. Twice hydrogen plus 3 hydrogen gives us 4 helium plus 1 neutron and some amount of energy. Furthermore, the fuel for nuclear fusion reaction is abundantly available as deuterium can easily be produced in plenty from ordinary water and tritium can be produced abundantly by joining the fusion neutron with light metal lithium, whereas both ordinary water and light metal lithium are also naturally abundant. The fuel supply is abundant. Deuterium occurs naturally in seawater and tritium could be bred within a fusion reactor from lithium, which is also naturally abundant. Hence, nuclear fusion has the potential to produce infinite amount of energy. In order to take place the nuclear fusion, the fuel, that is deuterium and tritium, must be heated to very high temperature of about 100 million degrees Celsius, where the fuel gets ionized into hot plasma of nuclei and electrons and provide sufficient energy to fuse. The hot plasma must be reserved long enough for fusion to occur and also to avoid damaging its contaminate vessel. Magnetic confinement is the most advanced confinement technique used so far, where strong magnetic field holds the plasma in a containment vessel. Classification of neutrons. Neutron is a chargeless atomic particle with a mass of 1.67 multiplied by 10 to the power minus 27 kilogram that was discovered by Chadwick in 1932. Neutrons are usually produced during fission chain reaction in nuclear power reactor. A nuclear fission reaction always depends on the energy of the neutrons. On the basis of kinetic energy, neutron can be classified in various categories. Number 1, cold neutrons having energy less than 0.003 electron volt. Second, thermal neutrons having energy in the range of 0.003 to 0.4 electron volt. Third, epithermal neutrons having energy in the range varying from 0.4 to 100 electron volts. Fourth, intermediate neutrons having energy in the range varying from 100 electron volt to 100 kilo electron volt. Fifth, fast neutrons having energy varying from 200 kilo electron volt to 10 mega electron volt. Lastly, high energy neutrons having energy greater than 10 mega electron volts. Neutron sources. Neutrons could be produced from various sources such as including alpha particle induced fission, spontaneous fission, neutron induced fission, accelerator based sources, spallation neutron source, photoneutron source, and nuclear fusion. The interaction of neutron with the matter or atomic nuclei results in different consequences such as neutron atomic nuclei interaction, in which energy and momentum neutrons remains conserved, that is elastic scattering. Second, neutron atomic nuclei interaction, in which momentum of neutrons is conserved but not energy. This is inelastic scattering. And lastly, neutron atomic nuclei interaction, where nuclide captures the neutrons, resulting in the formation of new nuclide or other nuclear particles. This may be referred as spontaneous fission. Before discussing nuclear interaction with the matter, students, let us discuss about the neutron flux. The product of the density, that is n, and the velocity v of neutrons, called as neutron flux, denoted by phi n, is equal to the product of n and v. The density of neutrons, defined as the number of neutrons per unit volume. Neutron flux can also be defined as the number of neutrons traveling through a unit cross-sectional area in unit time at right angles to the direction of the neutron beam. In general, neutron flux includes all the neutrons traveling in all directions and can be defined as the number of neutrons consisting a sphere of unit volume in unit time. Sometimes it may be referred as the current when neutrons are traveling in one direction only. Generally, the neutron flux accounts all the neutrons traveling in all directions and defined as the number of neutrons crossing a sphere of unit area in unit time. Hence, the total energy flux can be described by taking the integration from 0 to infinity of phi as a function of EI with multiplied by DEI, where phi as a function of EI multiplied by DEI is the neutron flux within the energy range of EI and EI plus DEI. The neutron fluence, defined as the number of neutrons traveling unit cross-sectional area for a specified period of time, and is nothing but represented as the product of the quantity N multiplied by V multiplied by T. Generally, the term cross-section is defined as an effective area in which certain interactions between incident objects and target objects are occurred. However, in nuclear physics, the neutron cross-section is defined as the measure of degree to which atomic nuclide can interact with the neutrons of certain energy. It is noteworthy that neutrons cross-section is not related to the actual physical size of atoms. The distance covered by the neutron before being stopped depends on neutron energy and cross-section of the material through neutrons are traveled. For better understanding, we may consider a simple case as shown in the figure. When a neutron beam of intensity I is impacting on a material having certain thickness W and unit area, the intensity I of the impacting neutron traveling beyond the thickness W will be reduced depending on the number of nuclei in unit volume, that is N prime, and the macroscopic cross-section area, that is N prime multiplied by rho of the material. Hence, the absorption equation can be written as I is equal to I naught exponential minus N prime multiplied by rho multiplied by W. The above equation represents that the total effects of nuclei N prime in the direction of neutron beam and the power of nuclei for interaction. This equation is specifically for one kind of interaction, where the absorber material has only one unique type of pure nuclide. However, the material could be made of various kinds of nuclei. Hence, in order to get the overall neutron cross-section, we should add all the neutron cross-sections for all possible reactions. The neutron cross-section plays a very important role in the selection of reactor materials coupled with each other considerations. Generally, the neutron cross-section does not depend on the type of reactions such as alpha particle reaction, fission reactions, neutron capture cross-sections, and so on. The total cross-section defines a linear addition of all the neutronic reactions occurred at the specific neutron energy level. The typical values of neutron microscopic cross-section, that is S, are typically between 10 to the power minus 22 and 10 to the power minus 26 centimeter square, and it generally measured in barn. Nuclear fission products. The variation in total neutron cross-section of elemental boron with neutron energy is shown in the figure, where the total cross-section decreases with increasing energy. However, this is not always true for other nuclides. For example, in the figure below, the total cross-section on 55 Mn increases with energy evident from this figure. So students, let us summarize what we have learnt in this module. In this introductory lecture, we introduced the nuclear energy and conferred its importance in the modern civilization. Here, we provided detailed information about nuclear fusion, nuclear fission, and various chain reactions. We also discussed some nuclear physics fundamentals such as half value thickness for neutron beam attenuation, nuclear cross sections, neutron flux, and fluence, and various other concepts. Thank you.